Is it clear? So in this clip, we're going to be going over some examples on how to calculate, evaluate limits, different kinds of limits, rational functions, trig limits, and also limits of piecewise defined functions. Before we start, there's just one little quick arithmetic of involving infinity I'd like to go over. So foundation, we're just going to call it foundational procedure. It's good to know how to do this. Let's see that you had a number. Let's say you had 3 divided by 0 positive. What does this mean? 0 positive means an infinitely small positive number. For example, 0.00000000000, as far as you can get 1. Okay, an infinitely small positive number. What happens when you reciprocate an infinitely small positive number? You get an infinitely large number, right? So another way you can look at 3 over 0, so that from the right is the same thing as 3 divided by 1 over infinity. When you divide 1 by infinity, you get an infinitely small number, which is exactly the same as this. So what I'm saying in essence is 0 from the right is the same thing as 1 over infinity. Okay? So if I do this algebra right, if I do this algebraic manipulation here, I multiply by the reciprocal 3 times infinity over 1, the final answer will be infinity. Okay? Now what if I have 3 divided by 0 from the left? What is 0 from the left? It is negative 0.000001, an infinitely small negative number. Okay? How can I express that using infinity? To express an infinitely small negative number is basically 3 divided by negative 1 over infinity. Okay? So it's just the opposite of that. So this is equal to 3 times negative infinity, which equals negative infinity. Alright? So what I'm saying in essence is anytime you have 0 from the left, you can replace it with negative 1 over infinity. They mean exactly the same thing. An infinitely small negative number, as small as you can possibly get. Okay? Alright, and also another thing I want you to remember is the sandwich theorem for sine, which basically tells you that the limit as x approaches 0 of sine x over x equals 1. Okay? I have a clip that goes over the derivation of this so you can verify this with the calculator. Alright, let's go ahead and try some examples. Okay? So for the following examples, the instructions are to evaluate. Okay, evaluate. Number 1, evaluate the limit as x approaches 4 from the right of 3 over x minus 4. Okay. Alright, to do this, we're going to plug in 4 from the right into this expression right here, which is equals 3 over 4 from the right minus 4, which equals 3 over 4 from the right minus 4. You have a very small positive number, which is 0 from the right. Okay, so remember what we just talked about? 0 from the right is the same thing as 1 over infinity. Okay, so this is 3 over 1 over infinity. My 1 over infinity is kind of off center. Let me write it again. So, sorry about that. 1 over infinity. And then you can multiply by the reciprocal, 3 times the reciprocal of that, infinity over 1. And your final answer is infinity. Okay? Alright. Had it been plugged in 4, you think that the limit does not exist because you have 3 over infinity, but the directional limit here exists from the left or right. But the double-sided limit in this case does not exist. Okay? Number 2. What is the limit as x approaches 0 of sine 5x over 3x? Okay? Now to do this, you have to be really careful. Remember, using the sandwich theorem, the variable for sine and the denominator have to be identical, right? But if you notice in this case, the value that you're taking the sine of and the denominator are not identical, so we have to address that, okay? So I'm going to use the constant limit rule for limits to do the following computation. So I'm going to write this as limit as x approaches 0 of 1 over third times sine 5x over x. Now the constant rule allows me to factor out the constant out of the limit because it's independent of the direction of x. So it's going to become 1 over 3 times the limit as x approaches 0 of sine 5x over x. Now the goal is I want to make this sine argument identical with this denominator right there. So how do I accomplish that? So I know that this is 5xy, I need is a 5 here. So how do I introduce 5 to this expression without changing the expression? So all I just do is multiply by a variation of 1, namely 5. So multiply by 5 in the numerator and the denominator. So multiply by 5 over 5. Okay? Alright, I'll use the constant law of limits to factor this 5 to the numerator here, and then this 5 is just going to go to the denominator there. So I'm going to have 5 over 3, this one getting tossed up to the front, times the limit as x approaches 0 of sine 5x over 5x. Okay? Alright, you can now see that the limits are both identical. Alright, so if we take a look at this limit right here, it's similar to the sandwich theorem, just like I just said. But we have to be careful. You notice in the sandwich theorem that the variables and the limit, the value of the limit are identical. That's a requirement in order for you to use the sandwich theorem. So let's take a look at this case we have here. This is 5x. 5x, they match, which is good, but they don't match, it doesn't match with x. So we need to fix that. So the question is, as x approaches 0, what does 5x approach? Is it obvious that 5x approaches 0 as x approaches 0? Obviously, right? Because 5x is 5 times x, and as x gets really, really close to 0, this whole expression is just a multiple, is 5 times that value, so it also approaches 0. So 5x approaches 0 as x approaches 0. Okay, so that's the bottom line there. So in this case, let's just write down the remark. We'll just say that as x approaches 0, 5x also approaches 0. Because 5 is a multiple of what this value is approaching, which is 0. So we can rewrite this limit as 5/3 of the limit as 5x approaches 0 of sine 5x over 5x. We can see that this and this all match. So now we can say we can make a substitution. We can say let u equals 5x. So now we're going to have 5/3 times the limit as u approaches 0, as u approaches 0 of sine u over u. Okay? Equals, now we can now use the sandwich theorem. This whole limit is 1, 5/3 times 1, and then your answer is 5 over 3. Okay? Now, this u substitution just makes it clearer to see how this limit is in this formulation. If you do not want to make this u substitution, you can go from this right to here. You know, it's also correct because the where limit is approaching and then the arguments of sine in the denominator are identical, so that gives you the right to make the substitution. But I did this just to make it obvious or clear that it matches perfectly with the form of the sandwich theorem. So it always has to be in this form. This variable and the numerator and the denominator have to be identical before you can use the sandwich theorem. Alright, now let's move on to question number 3. In question 3, we're supposed to find the limit as x approaches pi over 2 from the right of secant x. Okay? Of secant x. Now, if you know what the graph of this looks like, you can do this limit in a snap. But let's do it algebraically, and then I'll show you how to determine this limit uh, graphically too. So I'm going to use my identities rule, my reciprocal identity, to replace secant. So I'm going to have limit as x approaches pi over 2 from the right of 1 over cosine x. Okay? Now I'm going to make a substitution. We're going to have plug in that limit. So it's going to become 1 over cosine of pi over 2 from the right. So the question is, if you're approaching cosine pi over 2 from the right, what value is this whole function approaching? I know cosine pi over 2 is 0, right? But if you're approaching it from the right, what direction is that 0 approaching? Is it a small positive number or a small negative number? That's the question. So let's sketch the graph and take a look at what happens with cosine around pi over 2. Okay? So let's assume this is pi over 2 right here. You should know the graph of your cosine function. It starts from the max, and then it goes right through pi over 2, and through pi over 2 this way. Okay? Alright, so if you notice, if you're approaching pi over 2 from the right side, okay, approaching from this direction is pi over 2 from the right. If you're approaching pi over 2 from the right side along this function, what is happening? You notice that you're going from the bottom up. You're going from the bottom up. So you're approaching a really, really small negative number. Okay? Because if you're approaching from this direction, it's 0 from the left, right? 0 from a negative number. And then if you're approaching from the top, it's going to be 0 from the right. Okay? So we're getting really, really close to a very, very small negative number, right? So we can say like around here is negative 0.5, and then as you get closer, it's like negative 0.05. So it's getting close to a really, really small positive number, okay? So 1 over cosine pi over 2 is the same thing as, from the right, is the same thing as 1 over a very, very small negative number, since we are approaching from the bottom. I didn't mean we are approaching from the top, it would be positive, okay? So what is 1 over a very small negative number is the same thing as 1 over the reciprocal of negative infinity. If I drop, change, flip, or multiply by reciprocal, I have 1 times negative pi over 1, multiply that out. The final answer is negative infinity, and there you have it, okay? Now let's take a look at the graph of secant theta using a graph. It's a piece of cake to deal with the graph, using the graph. But it's a painful graph to sketch. That's why most people won't like to use it, but if you know what the graph looks like, it's a breeze. Okay, so let's sketch the graph of secant theta real quick. And then we're going to use that to determine what the limit is, alright? So, I normally generate my graph of secant using cosine, since cosine is a reciprocal of that. I just sketch my cosine graph, and then I use it to draw my my secant graph, okay? So let's just say this is pi over 2, and this is pi, right here. So sine starts from the numerator, starts from the top. I'm going to make it dirty, right? It goes right through pi over 2 down to pi, something like that, okay? So that's what the standard cosine graph looks like. Everybody knows what a cosine graph looks like. If you don't, you might want to go and review it, okay? Alright, so for secant, there is an asymptote whenever cosine is 0. So cosine is 0 at 2, so we have an asymptote right there. So I'm going to draw my secant curve in green. So it looks something like this. Straight up, like that. It's an asymptote right there, and then down here, oh sorry, from right here, it goes straight down like this, and there's an asymptote right there. Okay? So the pattern just continues forever. Like it goes up like that, makes a U in the other direction, something like that, and then this one makes another U here. And then the pattern just continues on and on and on forever. Okay? Anyway, what we care about is as it approaches pi over 2. You notice that this is this function has a discontinuity here. So as you're approaching from the right, as you're approaching power 2 from the right, what value is the function approaching? You know, it's going down forever, down to where? Down to negative infinity. So this makes it obvious that as you're approaching power 2 from the right, the function is going down to negative infinity. So this shows that the limit as x approaches power 2 from the right of the secant function. We're looking at the green one now. Okay, don't get confused. We're looking at the green one. As this green function approaches this vertical asymptote from the right, it dips down forever to where? To negative infinity. So there goes your answer using the graph. Okay, same as that. Alright, now let's take a look at question number 4. Question 4, it's an int function. We're going to take the limit as x approaches 0 from the left of int x over x. Okay? Alright, so go ahead and plug this in. 0 from the left is a really small negative number, so we're going to be looking at the int of 0 from the left over 0 from the left. So int is basically known as the ceiling function or the greatest integer function. It rounds every number, every non-integer to the next integer that's bigger than it. Okay? So for example, let me just write some examples for you. Int of 1 is just 1 because it's an integer. Int of 1.5 is 2 because the next integer bigger than this number right here is 2. It's not an integer. If it's not an integer, you just round it up. Okay, and then int of 0.5 is 1 because the next integer bigger than this fractional number right here is 1. Okay, so it's called a ceiling because it rounds up. Alright, so if you take a look at this, what is int of 0 from the left? So it's basically int of, you can use an sample number, right? Int of 0.000, a really small a really small negative number. I gotta be careful. Really small negative number. Okay? So if you round up a really small negative number to the left of 0, what is that going to give you? If I want to round this number up, the next integer that's bigger than a really small negative number close to 0, if I round this up, I'm going to round it up to 0. Okay? Just to illustrate for you, if I draw my number line, this is 0, and this is 0 from the left. So if I round it up, this is rounding up, it's going to go to 0. If I round it down, it's going to go to -1. So this numerator here is going to be rounded up to 0. So what you're going to have, int of this is going to be 0, strictly 0. That's what the int function does. It rounds up numbers divided by 0 from the left. What is 0 from the left? Is an infinitely small negative number, so divided by -1 over infinity, and drop, change, flip, or multiply by reciprocal, which is 0 times negative infinity over 1. Negative infinity times 0 is 0, so your answer to this function is 0. Okay?